all amplitude will be something changed. That will be your A dash. Here it will be your cos 2 pi FCT plus theta. There is no switching involved here, just see. And you know what is the value of this theta, because this you are taught in your second year also quite a lot. So you will be able to find out. I'm giving the value. What is this theta? It is like that, twice pi divided by the lambda wavelength. Wavelength will be what? Okay, speed of light divided by fc. Lambda into fc becomes your speed of light that way. So that way, twice pi by lambda into path difference. This path difference will be your L. And this becomes your phase difference theta. Okay, twice pi by lambda into L. L can be very small, micrometer or something, even picometer, whatever is saying, but accordingly this phase is changing. Now question comes that if the frequency is such that this lambda becomes small, frequency is very high, that is lambda becomes small, so theta will be larger. I am interested in that point when theta becomes equal to pi. L is fixed, lambda is fixed. Okay, L is fixed, lambda is changing according to applied signal. So L by lambda into 2, that should become your pi. Okay, if it becomes pi, then what will happen? That this cos 2 pi FCT that we are feeding here, by the time it comes here at this point, its phase is changed pi. So it will not go outside, it will return back now. It will become a negative magnitude now. So it comes up to this point, it returns back. So at the output, you are not getting any signal. So this time delay, which is called as transit time. Up till now, there is no switch involved, okay? Transit time. So device itself, for example, MOS transistor cannot be used for microwave kind of amplification or application, because by the time it reaches at the other end, its polarity is changed, so it returns back. We want that theta has to be smaller than pi. Okay, theta has to be smaller than pi, going up to L. But by the time it goes to L, this pi phase shift has taken place at this point itself. For example, frequency is very high, lambda is very small, so pi radian phase shift takes here, so it returns back. So transit time effect says that signal cannot go at the output. So this is the limitation of the device. Nanotechnology is even faster than that, so it cannot reach the destination point or your measurement or so your experiment fails. So accordingly, if you are designing your frequency for increasing, then this path length L also has to be decreased. If this is decreasing, okay, if this is decreasing, then this also has to be decreased, so that it comes from here to here. It will not be pi, it will be some phase shift. It will not revert back. So that will be your transit time effect. It was happening in valves earlier, but it happens in transistors also. So transit time effect is taking place in transistor solid state devices also. Okay, this is about the limitation of the device. If it is understood, I can go for the switch now. Is it okay? So you have to select, select a device which has got the transit time. Okay, transit time it should be smaller. Transit time should be smaller. Okay, so that device you have chosen, and then you will be working for the switch. When you want signal to enter that, when you want signal to be stopped there. So transit time effect has to be taken care first, then coming to your switch. Is that okay now?
Yes, sir.
Okay, fine. So now I'm coming to your next page. Next page is here again. Yeah. Here what happens when you want to control a switch, you have to give a signal which will make the switch on. Okay, and what is that? When no control is applied, okay, switch is off. Okay, when switch becomes on means here you apply a voltage here, DC voltage. This I'm calling as V. A DC voltage V, positive V, you can write it as positive V. I'm applying a positive voltage to the control terminal of that device. It is a three-leg device now. In the control leg, you are giving this. So transit time effect has been taken care, but I want that to be controlled when the signal should pass, when the signal should not pass. So I'm applying this voltage plus V. Plus V I'm applying. Whenever it is applied, switch becomes on and the signal starts going to that point. Okay. Now I want signal to be off. Switch to be off. Our output signal should not be going over there. So that way it is what? I'll be adding this thing, a voltage here, minus B. It is T, it is time axis, remember that. I'm not writing that, you can understand better. So here, if V has been added, switch becomes on. At this point of time, minus B has been added. So what is the result now? Here what happened? Here switch got my voltage up to this point plus B. Now it has become minus B here. Okay, and then it becomes 0 because unit step function. It is negative unit step function. It is positive unit step function. The two are added together, and this we call it T1 and T2, and amplitude here is your V. This we call as a pulse. Remember, pulse is always combination of two, what you call your unit step functions, positive and negative. Only then you are getting a pulse. Somebody is saying that this is the pulse. Here I am writing like that. Here I am writing like this. Here it will not be combination of two unit step voltages. So we cannot call it pulse. It will become some kind of a square wave or some other wave you can call it. Here is a time t. So pulse means it is going to some voltage V and becoming your 0. That is your pulse. It is combination of positive your unit step function and negative unit step function. This becomes the off time T2, T1 becomes the on time, and till what time the switch is on? T2 minus T1. During this time, signal will flow. After that, it will stop. Even if transit time conditions are satisfied, it cannot go to the output. So that is your switch. Is it clear up to this point? Then I will go ahead with your some references of your class 11th or so. Is it okay? Any doubt here? It is not a square wave. It is 0 to plus V volt. So you can say it is also known as a clock. 0 to 5 volt of a V volt, that is a clock. It comes on repetition after some time, we call it a clock. But if this kind of signal that we have given here, this one. Very long. Here, this one is not a kind of clock. This will be a kind of wave. It is having positive and negative both the amplitude, so it is a wave. It is not a clock. It is not a pulse. Pulse can be negative also. Means what? I can write a pulse like this. I'm writing a pulse like this. Here I have applied a negative voltage, and here I have applied a positive voltage. So this and this cancels. This and this becomes your -5, minus V. This is your 0. So 0 to minus V, it is going. It is also a pulse. It is a negative pulse. Positive pulse and negative pulse, both are there. But you are making like this, that becomes a wave. That will not be a negative going clock. You can have positive going clock. You are having both of them are operating on your system. So you should not be confused there. So pulse can be positive and negative both, but not a combination of positive and negative both. Is that okay? Any question?
Yes, sir.
Any student, don't accept whatever I'm saying. You raise your questions. You have read your many things earlier. So anyway, this is the one. Now I'm coming to a capacitor that you are going to charge. Your class 11th result I am going to talk to you now. Okay? Class 11th result is, it's not seen there. Okay. Class 11th result. You have seen a low pass filter and a high pass filter. Both the things are used in the switching circuits. Okay. I am just making the basic discussion over here. Here is my capacitor C. Here is my R. And this is the output. Okay. I am giving a pulse here. Single pulse I am giving. I can make it 2 pulses also. Doesn't matter. I can train a pulses also. 2 pulses I have given. Both are same width. Width is not changing. So remember, pulse width is same. Just 1 second. Welcome. So this is the one I have given 2 pulses. Okay. You can make it single pulse first and see that if this pulse is applied to this. Where is that? Here. Applied to this point. Applied to this point. And I'm making observation at this point. Okay? Can anybody tell me what is going to happen at the output? How does the output come? This capacitor is having value C, this is having value R. And here it is 0, and here it is V volt. Here it is 0, here also it is V volt. Width of the pulse is same, that I'm not contradicting, like that. So what is going to be the output? This output I'm putting here as V naught T across the R. What is this filter? It is a high pass filter. You remember that? No doubt, it is a high pass filter I'm giving. So what happens when I applied the first pulse? This pulse I applied at this T equal, let us say T equal to 0, I'm talking, this is T equal to 0, T equal to T1, and here it is T equal to T2, and this is your T2 plus T1. So it is coming like that, T2 plus T1 like that. I have applied this. So what is my V naught T? V naught T, let me plot. V naught T is across the resistance. This I am plotting here. That's what I said, it is all conceptual. That time constant is R into C. So I think you already know about that. So V naught T will be what? When I have applied T equal to 0, okay, this plus V will be applied across the capacitor. Okay, plus V is applied here at this input and it will appear as a short circuit here. So plus V comes here. Okay, so here what happens? Plus V comes here. V naught will be plus V. Plus V or minus V? Plus V is put over there. There is nothing like charging taken place. So plus V comes over here. The plus V will be plus V. Okay. After that, that plus V is remaining at this R and C. So C will start charging through this R. C will start charging through this R. So what will happen? This voltage across C here, will that be positive or negative? It would be reducing, negative, because this will be, you are charging it now. So this will be positive, this will be negative. So it will be reducing, and as a result, it will keep on decreasing like that. It is according to time constant RC. Okay, now T1 has come here. I have not gone to all these stages. T1 has come here. At this T1, this negative voltage minus V is applied. So what will happen? V has been reduced to some value, and here there will be a minus V added to this value. Let us say I'm saying here V dash. This one will be your V dash minus V. So this voltage at this point, when I have gone below that, V dash is some value significantly high. This will be hanging at some point here. It will not be coming at minus V directly, it will be coming somewhere else. V dash minus V. I am here. Okay. After that, this pulse is gone. So charging is not taking place. Okay. Capacitor charging is not taking place. So what happens? It will start discharging. It will start discharging. Capacitor will discharge through this R like that, and because of that, it will keep on rising according to our exponential, that time constant once again. Okay, so it has gone to this, and now it has gone here. So that way it has come. It will come up to the 0. If your width T1 minus T2, that is large enough, it will become 0 much before that. Your T2 might be somewhere here, doesn't matter. Okay, so it becomes 0 over there. So your high pass filter, it is going to the maximum value, and then it discharges. It is charging, in fact, charging going in a negative direction. This part is negative, that is positive that way. So V naught T will be the subtraction of that capacitor charge, and it is reducing now. And all of a sudden, on the second, here, the pulse negative amplitude applied, it jumps by that. So this value is from here to here, it will be your V. It will be your, I can say minus V or V, but from here it drops by V. So it is coming at this point. It is charging like that. Is the high pass filter clear? If I'm making a switch with high pass filter configuration, what are you going to see? Or any doubt? Conceptual, don't hesitate, ask the question, because capacitor, you know, when you're charging, it charges, because this side is positive, this side is or this side is positive, this side is negative. That way it will be charging. So this negative voltage is increasing this side, and as a result, this output is decreasing according to that. Okay, so that's what it is coming as a high pass filter like this. So, what is the suggestion? Shall I go ahead or it's okay? Students, don't hesitate.
Yes, sir, we have understood.
Understood now? It is class 12. I mean, theory. So I am just putting as a revision because when you go to the switches, this will be your. Now I am going to do that with your low pass filter. Okay. This was with the high pass filter. Now switch is applied using a low pass filter configuration. Means what? Here is my. I have taken single pulse only. I can do it from multiple pulses also for your convenience. Here is 0. Here is V. This is 0. This is your V. And here plus V is added. Here minus V is added as a step. That's what this pulse has come. Now, this we are putting here. I am putting a resistance here. I am putting a capacitor here. This is my signal, and this is the one I am interested in, V naught T, that is going to operate my switch. So at what time the switch will be operated, how much delay will be there, that will be now very well designing that yes, it is sustaining that particular frequency of the clock or not. Okay, so that is the one. I'm coming to this now. R and C, same thing. Here is my R, here is my C, this voltage is applied. In this case, what happens? I am plotting here V naught T. It is 0, here it is T1. Other pulses I can take later on. This is 0, this is T1. So when plus V is applied, that V will be appearing at this point, output point or not? No. Whatever comes as a current drop here, V minus this current drop, whatever voltage comes here, that will become 0. Is that clear now? So initially when this V has been applied, this V naught T becomes your 0. So here it is your 0 at T equal to 0. Convinced or not? T equal to 0, it is at that point, then it remains, voltage remains V. So V voltage will be now charging the capacitor through this resistance. Okay, and it will be charging through this exponential way up to this. In fact, I can say this will become a V. By the time I have come to this point, it has become this V. Charging time constant, how much voltage it is going, accordingly we are doing. If I am making V, then it will be exactly V. I think it's up to you to modify that. Now this negative voltage V is applied at T equal to T1. So what will happen? I am here. This one will be coming to this point. Okay, this will be coming to this point. That means what is that? If this voltage was V, then it will be coming to the 0. If this voltage is less than V, then less than V, V dash minus V will come over here. That is the voltage here. Okay. After that, what happens? This capacitor will start discharging because voltage, the pulse is gone now. The capacitor is starting discharging and it will go according to the same thing, time constant like this. Your T2 might be somewhere here, or T1 might be somewhere here, T1 might be somewhere here. You can adjust like that. So that is the thing. So when the switch is becoming off, at that time there is a negative potential coming at the switch, and you have to see it is not going to damage the switch. Okay, but in the positive case, yes, you are within the limit. Your switch is working. So low pass circuit, your application of switch is safe, except for that this one, this tip is minimized like that. I'll tell you the procedure how to minimize these tips. But right now, that's what I'm explaining. What is my low pass switch and what is my high pass switch? Material of the switch is according to the transit time effect. Any question here? I welcome question.
No, sir.
Okay, fine. So now you ask only one person is saying, you are talking on behalf of everybody, so be sure that all of us are having the same view over there. Now, another thing, what way the time constant is controlling that. Okay. Here is the voltage. Here is the voltage that has been charged and it is discharging like this. Okay, and when it has become zero, then the negative step has come and it has become like this. It becomes like this. Now I'm changing the time constant now. So the result becomes something like that. This is my V naught. Magnitudes you can compute according to that, the way I have given the idea. It is like that. When it is happening, when decay is fast and making it here, pulse width, Tp is a pulse width, T1 minus T0. Okay, Tp is a pulse width. If Tp divided by this time constant RC, okay, if it is greater than, much greater than 1, you are having this kind of shape. So our time constant you have to accordingly choose to make your switch. Convinced or not?
Sir, can you repeat it again?
See, RC I have given, that is your low pass filter I have used like that, not high pass, I'm talking low pass right now. So when it has gone, it was charged at this voltage, and after that voltage, it starts discharging because capacitor is not taking charge. RC is very large, time constant is very large. So before the tau p arrives, it will start falling down. So it will become like this, and it will come up to this point somewhere in between. My pulse was somewhere here like that. Now when the pulse is applied, it was 0 by that time, so it will become negative. And negative, again it will start discharging, negative voltage will start discharging through this RC, and it will fast decay. So e to the power minus t by RC you are putting, if RC is large, it decays faster. You already know that. So Tp by RC is greater than, much greater than 1, it will decay faster like that. If Tp by RC is other way, Tp by RC, okay, is less than, equal to 1, okay, that means RC is much larger than this tau p, so discharge is not taking place. So during this time, it remains a constant voltage. So like that, you are going to get like this, yeah, and then you are going to make like this. Oh, this is not there, of course. This is the one you are making like this. So now you know what is the challenge for making the nano switches. Okay, you can make it some other way also. This one, instead of making like that, this one will be decaying like that. It has gone to something, some lower value, and then it has gone like this. So this is when Tp by Rc is smaller than 1. The pulse width is smaller, time constant is larger. You are getting shape like that at the output. The pulse width is larger, time constant is smaller, then you are getting this kind of fast decay. And is it going to damage your switch or not? That is up to you to decide. Okay, should I wind up here with first day?
It is
something,
okay.
Something more or okay for today?
No, okay for today. It's okay.
All students, please, still time is there. I'm waiting for your questions. Becoming on and off. It is not always on and off. Sometimes it becomes, the two are stable states. On and off is stable state. There are certain cases that on state and quasi-stable state, both are possible. So off state and quasi-stable state, half stable. Okay, that will be there. One off is stable, on is quasi-stable, and there will be third one in which both the states are unstable. So that way the switch will be working. Switch right now I have taken, it is two stable states. I will call it bistable. Okay. So in due course of time, I will talk about quasi-stable state. You may know in terms of monostable switch, and if it is unstable in both the cases, it becomes your astable state. So these things I will talk later on. For today, it is okay. So we close now. So good day, all of you. Good day, all of you. See you again.
Thank you, sir. Thank you, sir.
Monday I might be missing your class. Professor Gupta will manage that way. So Monday I might be out of station.